Okay, so the next talk is given by somebody that works at a company. He claims that most of the world's population touches their product every day because their product is the surface of a cell phone screen, among other things. So I'm going to introduce Zhang. He's the business development director at Corning. And he's going to be talking about their last innovations for MEMS applications.
Thank you. So there is a clicker, right? Okay. So Paul, you may be the only one in this audience that has actually used Corning glass. If there are others, let me know. Yeah, so I'm going to discuss, this is switching gears in a big way. So far, I've only heard silicon being mentioned. And a glass wants to play kind of a complementary role to assist silicon maybe do a better job in some cases in MEMS applications. And so some of the new things that we've done recently, I'd like to cover a little bit. And then there's some stories about what role glass actually played in the very beginning of MEMS. Which key moves this one? Okay. Oops. Oh, it's the green. Okay. Sorry about that. Yeah, so a little bit about Corning as a company, and then glass in current MEMS devices, and then what glass can be changed or improved to help silicon deliver maybe better performance for MEMS devices. And specifically, I'm going to be talking about hermetic bonding between glass and silicon, as well as fusion bonding. And you'll see the difference pretty quickly, and then I'll conclude. This is actually a joint presentation with SUSE Microtech. I know the litho group is here, but the bonding side of SUSE did some of the work with us. So I want to acknowledge their contributions. A bit about Corning. It's a very old company. I wish there was a competition for how old, the employer is, and we would probably be one of the winners. Almost 170 years old, and we're headquartered in Corning, New York. It's about 7 hours of drive. And people who travel from New York City to the Niagara Falls travel through Corning, and there's a very nice glass museum. So if you stop by, take a look, and there's fairly nice glass stories being told inside the museum. $14 billion of sales last year, and we're one of the Fortune 500 companies. And this is actually the headquarter building built, I think, in 95. And this tall tower used to be where they do the thermometer tubing. And so this is preserved to kind of reflect on Corning's history and contribution to society. And I was joking with Paul that even though this headquarters building is all glass, including the staircase inside, but there's no Corning content because we don't make thick glass like you see here. And so there's zero Corning content in the headquarters building. But you do know Corning by, like Paul said, by the phone cover that's on most of the high-end cell phones today. And we brand this glass Gorilla Glass. So it's gone through 6 generations. And now, I think beyond Gorilla Glass 6, we now call the glass Victus. So there's now Victus and Victus 2. So the latest generation on non-Apple phones is Victus 2. And then on Apple devices, it's actually not a piece of glass. It's a piece of glass ceramic with tiny crystals inside. So the drop performance is even better than Gorilla Glass. So there's a lot of interesting stories on the web if you want to look into some of the details. So this is about Corning, and I'm actually part of a group that turn a piece of glass into wafers. So we have several product lines doing MEMS packaging in the case of a wafer level capping. And wafer level optics is where we actually build optical devices on glass. And some of the Face ID components are based on Corning glass, where you build structures to do different things to allow 3D sensors to work. And then a few people yesterday mentioned augmented reality, and Corning is one of the players in constructing waveguides on high index glass to allow you to view things with an interesting field of view. And then for packaging and other things related to semiconductors, we offer glass with different CTEs and different properties to allow people to package silicon-based devices. So that's about the company. So where does glass fit? I was able to find cross sections of different devices that you can actually buy today. And many of you are much more familiar with these devices. So glass typically is bonded to silicon to provide a hermetic environment. And many of the MEMS devices rely on the environment being stable and sometimes controlled moisture and things like that. So you see glass in accelerometers, pressure sensors. The optical scanner here is actually a window that covers a MEMS device. And this window sometimes is in a dome shape, sometimes it's in a slanted angle configuration to allow minimum reflectivity when you have a beam coming in and the MEMS mirror redirects the light and coming out of the cavity. And then the last one on the bottom right is actually I think there's a representative from Menlo Devices. They actually make MEMS devices not on silicon, but on glass. And they also have what's called through glass via, that the orange part of the structure to conduct very high frequency capable signals through glass, which leads to very high performance in high frequency scenarios. So glass is already in use. And so what's new, right? So I'm going to introduce a little bit about how glass behaves when you want to bond it to silicon and what we can do to maybe change the way bonding happens and change the way stress is in the final device. And Paul wanted me to actually introduce a little bit about glass forming. So most people think about glass melting, but forming is a critical part of making glass. You can melt glass to be uniform and ready to be made into different shapes. But how you form a flat sheet of glass is actually critical to the attributes of the sheet that you get. So I have 4 examples here. At the top left is your window glass manufacturing process, which is called float. So you actually have the orange colored liquid tin where glass is spread into a flat sheet. And this is 1,000 tons a day, right? Huge volume. And this is why you can get big windows pretty inexpensively. So typical application is window glass, or your automotive windshield is also made using float. Top right is what we call a rolling process. You have a pair of rollers and you feed molten glass into the gap between the 2 rollers, and then you can roll a sheet that way. And typical application is your cooktop. And it's not optical in surface quality, but it's good enough for cooking applications, for example. And Corning's Pyrex, you might have heard Pyrex. This was the original borosilicate invention that Corning made, was made using this rolling process. And then on the bottom left is a very thin glass that we can draw using what's called a down draw process. You can actually see the brownish looking glass going through a slit, and then it forms a sheet. The downside of that is the glass is in contact with the inner walls of the slit. So sometimes there's imperfection coming from this contact. And bottom right is what's probably most relevant to this community. This is Corning's fusion process. And if you look at the cross-section, it's an overflow system where the glass overflows a trough, and then the glass recombines at the bottom of the trough. So the outer surface of the glass sheet has never been in contact with another material. So you get pristine surfaces with very good thickness uniformity. And we can make this now really, really big. The bottom right chart shows how you get your LCD TVs now, 80 inches in size, because the mother glass is actually 2 panels of the window glass here, right? And almost 3 meters in width. And you can draw it to any length you want. But I think in order to fit a big sheet of glass in a piece of equipment, whether it's a PCVD or sputtering, you have to cut it to some size, and we typically cut it to about 3 meters in size. So you can cut big TVs out of a mother sheet like that. So fusion is very interesting because we can make glass not only big, but extremely flat. And imagine you can cut wafers out of a big sheet like that. And any size is really possible. So switching gears again from sheet forming to bonding of glass to a silicon wafer. So I said the hermetic sealing is often required for MEMS applications. And there are many ways to bond a silicon to a piece of glass with the hermetic performance. And I've listed 4 more common ones. Anodic bonding is relying on high temperature and the glass producing a mobile ion, mostly sodium. And if you apply a voltage, then the sodium it moves, and the oxygen moves in the other direction, and the oxygen can combine with silicon to form a silicon dioxide at the glass-silicon interface. And that's how you form a hermetic seal. So this is very commonly used in the MEMS industry. A fusion is a different process whereby making the glass and silicon extremely flat, you can actually bond without anything and no voltage, and the glass doesn't have to contain mobile ions. So for people who don't like sodium anywhere in the device, this fusion process is maybe preferable because you can achieve the same bonding properties without the glass containing sodium. So I have 2 slides on fusion and a few slides on anodic. And then the other 2 commonly used methods is eutectic or glass frit. So essentially you deposit a material that melts at certain relatively low temperature, and then you can form a hermetic seal by the 2 materials mating with each other. The pluses and minuses are listed here, and I won't go through the details, but the beauty of anodic bonding is the surface doesn't have to be extremely smooth, and you can tolerate some particles. So there's a wide process window that you benefit from. And then fusion is no alkali needed in the glass. So I'll be covering these 2 methods. First, anodic bonding. So again, this is 2 pieces of glass, 1 piece of glass and 1 piece of silicon in contact with each other, and you heat up the wafers to different temperatures to essentially mobilize the sodium in the glass. And then you apply a voltage and you drive the ions in one direction and the oxygen in the opposite direction. And I've listed the temperature range that you can use anodic temperature at. And we consider 350 to 450 C kind of the optimal window, because if it's on the low end of it, the mobile ions are not very mobile, so it takes longer time for them to do its job, and the voltage may be much higher. And then if the temperature is too low, the surface imperfection sometimes also leads to defects in the mating interface. And then if it's too high, your device may not like it. So we consider 350 to 450 kind of a sweet spot for anodic bonding. CTE, the thermal expansion coefficient, is critical when you bond at high temperature and then you cool it back down to room temperature for device usage. And this is kind of illustrates what happens if the thermal expansion is higher than silicon or the same or the lower than silicon. So if the glass CTE is too high, then the after bonding and cooling, you will have a curvature due to the glass essentially shrinking more than the silicon. And the opposite is true when the glass the CTE is too low. And in the middle, when you match the CTE precisely, the bonded wafer stays flat back to room temperature or any other temperature in between. So we want to choose the glass with the CTE precisely matched to silicon. And glass is beautiful because you don't have to limit the ratio of different elements like in a typical single crystal material. And so by putting different materials in the glass, you can modify the CTE in a very large range. So silicon in this case is one target. If you have another semiconductor material that you want to bond to glass, we can pick another glass that has this property for bonding. A little bit on CTE because it can be a confusing concept. You know, most people cite silicon CTE to be 2.6 ppm per degree C, but that's actually what's called the instantaneous CTE. This is when you vary the temperature close to room temperature a little bit, and then you watch the strain or the relative length change, and then you take the ratio, which is essentially the tangent, the purplish reddish looking line. So that's your instantaneous CTE. If you bond at a certain temperature and you cool back down to room temperature, what's more relevant is the green line. This is what's called the average CTE. So this is the overall shrinkage of two materials, and you really want the average CTE to match. And silicon's CTE is a function of temperature. It's a strong there's a strong dependence. And 2.6 that everybody uses is really only applicable in the room temperature range. If you bond silicon to another material at high temperature, you want the match to happen at the bonding temperature and not at room temperature. So this is silicon, and if we want to bond in the temperature range that I mentioned in the previous slides, you want to be in the green zone ideally, and then outside of the green zone, the yellow zone is still okay for bonding, but you may suffer either throughput or quality issues. And so we want a glass that matches the average CTE in the green zone. And the incumbent glass actually works pretty well in the low temperature range, but if you bond it at the ideal 350 to 450 temperature range, it's actually not very well matched. So you would expect some bow after you bond it and then cool down to temperature. So we decided to use a glass made by fusion and cut wafers out of a big sheet. And we want to leverage a unique characteristic of a fusion type of glass. When you draw a sheet in air and you draw it fast, the glass actually cools down very quickly, which leads to a quasi-static kind of property. The glass isn't in a thermodynamically stable state. So this gives you a CTE that you can tweak through annealing. If you heat the glass up to the annealing point for an hour or two, you actually densify the glass, and the CTE can be dropped by a certain amount. So if the glass as drawn from this process isn't a perfect match to silicon, we can add an annealing step and make the CTE match perfectly. So this is a little busy, but the red line or the orange line on top is the glass where we just draw it and without doing annealing. And you can see the CTE is a bit higher than silicon. So when you bond these two materials together, you have a bow. But if we anneal, the arrow is indicating after annealing, the CTE becomes the second highest line. I cannot tell the color here. And then the matching to to silicon happens at 350, which is in the green zone, the ideal bonding temperature. So we want to see what happens if you bond this to silicon at these two different conditions. And typically when you have stress, it's symmetric. So the bowl shape is very nice looking, as I show here. And then the magnitude of the bow, if the CTE is mismatched, you have 300 microns. This is a 200 millimeter diameter wafer. We have 300 micron bow. But if you anneal the glass and make the CTE match very, very good, it drops to less than 100 microns. So if your device is sensitive to bow, we have the means of changing the glass CTE to make the bow very small. And the quality of the bond is indicated on the left side. This is the acoustic image of a bonded wafer, and there's really no evidence of any voids or bubbles in the bonded wafer. And then the permanency of this bonding, typically we do a knife edge insertion from the seam. And if glass breaks, we know there's enough strength to indicate it's a permanent bond. And then we did some modeling, and the modeling largely can explain the bow reduction due to CTE match, but we didn't really 100% predict the direction of the bow. And the reason is when you do anodic bonding, I mentioned earlier, there's ion mobility. You actually have a layer of glass where the sodium is totally gone, and the CTE of that portion of the wafer is now essentially 100% silicon dioxide and not the original glass. So there's change in overall CTE due to the anodic bonding process itself, and that made the match, the theoretical match, less than perfect. And another reason we like this glass is this fusion formable glass that we call SG 3.3 Plus has the unique property of being able to have vias that we can change the shape of. And this is important because, as I said, some applications benefit from through glass via, and the ability to change the shape of the via allows you to metallize such vias with more flexibility. For example, if you wanted a hermetic seal in the metallized via, a necked shape allows you to do that much more so than if it's a straight via. So we like that. And then it's also, in acid etching, it's much faster than some other glass types, which means if you want to form vias, you can form vias at high throughput and low cost. And then the dielectric properties, a lot of people like glass also because the dielectric properties are much different than silicon. And if you want to low loss, high frequency glass sometimes does a better job than silicon in providing this kind of conductivity. Just 2 slides on this other alternative fusion bonding process. And this is a process where we essentially provide a very clean surface, very flat and clean surface. And when the silicon has the same properties, we can bond it without introducing any bond agent, essentially, and there's no voltage involved in the process. So Corning has another glass, also fusion formable, that's called SG 3.4. That has essentially a perfect match to silicon across the very wide temperature. And this means you can bond this glass to silicon at any temperature you want. And by keeping the glass extremely clean and the silicon extremely clean, we can do fusion bonding between the 2 materials with very good quality. In this case, we have 10 wafers, and we used a commercial bonder. If you don't do the initiation of bonding right, the number 1 wafer shows you trap a lot of air. But if you use the machine's initiation mechanism, 9 out of 9 came out bubble-free in the center of the bonded wafer. And the only defectivity you see is always at 5 o'clock or 9 o'clock. This is due to some handling defects when we made the glass wafers. So in conclusion, glass is already used in MEMS industry, and we have the ability to change the thermomechanical properties of glass. So if you want to design some MEMS devices with the low stress, for example, we can help you control the CTE of the glass to exactly match. Or if you actually need some stress for whatever reason, we can work with you too to make that happen. Fusion is another possibility if you don't like sodium in the glass for your application. And in general, we really would love to work with this community to deliver a glass performance for your devices. Thank you very much.
Boy, I love that fusion process. Okay, we have some questions here.
Thank you for your nice talk, Angelique Rayleigh from Tokyo Electron. Can you comment on the compatibility of glass wafers to run in a conventional foundry?
Oh, excellent question. Excellent question.
And what the challenges are?
The challenges are a lot of the equipment is looking for opaque materials, right? And the sensors, sometimes use red light, sometimes use near infrared. And so for glass to be handled in a conventional silicon fab, you really need to opacify the glass. So we have solutions putting either metal or some multi-layer coating to make it behave like silicon, so the silicon fab can handle it. And the second challenge is if it's a glass with aluminum or calcium, the front end, typically, they don't like that. So we put a silicon nitride coating all around the wafer to make sure there's no metal on the surface. Thank you for the question. Great question.
Yeah, I got a question on you said when you do the bonding, you got your alkaline depleted on the surface, a thin layer of silicon dioxide. You said that you're causing the mismatch, because silicon dioxide CT is almost zero, so you're causing on the wafer bowing.
Yes.
How thickness is that the depletion layers?
It can be on the order of a micron. I actually provided a reference where people did detailed modeling to see how the thin layer CTE can impact overall stress. So we have not done that ourselves, but there's literature that describes this. I can, yeah.
Okay, yeah, I probably going to. The second question for you is you're talking about SG 3.4. How that different from the quartz? The same as the quartz.
So I think you actually meant fused quartz or fused silica, right? That has a CTE of 0.5 ppm per degree C. So if you bound that glass to silicon, you're going to see a bow.
Hello, Karel Crote, C2MI. A little question. Well, we did use fused silica, burrow floats, or all those glasses for microfabrication. And well, the first question was to the point. It's one issue to make sure that we don't have any cross contamination throughout the fab. The other way that we have issues is actually in all the etching tools. We're having like electrostatic shocks. I'm just throwing you a curveball. Is there any tricks that you have found to actually have like a substrate where you can have that attraction still without having to cope at the exterior? You mentioned having a coating layer on top, that we can still use electrostatic shock for etching or for any deposition in high vacuum system. Do you have like some tricks down your sleeves?
Yes. So the same opacification technique that we have, it can either be a titanium film, which not only provides the opacity, but also the conductivity you need for e-chucking. Or, we have another formulation that has amorphous silicon providing the conductivity. So yes.
That included in the wafer.
Yes, it's, yeah.
We had to do it, right? So,
yeah, so talk to me, and we actually published a paper just with the details. Thank you very much.
Hey, wait, do you have a DEI story?
Oh yeah, so no, I have.
You have a mic.
Yeah, so I've been with Corning 20 years, and I think women scientists in Corning really do very, very well, right? The expert on the fusion technology is a woman engineer, and then the person who invented the glass ceramic cover is also a woman scientist. So in my 20 years, I've worked with top-notch women scientists who really rise to the very top of the scientific rank in Corning.
Thank you.